Hi everyone, I'm Riccardo Natale from DESI, and this is my contribution to Array Universe from home. And I'm going to talk about a model implementation of axion kinetic misalignment. So I would like to start briefly reviewing the standard misalignment mechanism, which is already a well-known mechanism to produce axion dark matter in the Array universe. And in this mechanism, we just have an initial condition for our axion field, which is our axion field is frozen at theta I, an initial value, and this value is misaligned from the minimum of the axion potential. And once the Hubble friction drops below the axion mass, then the axion field will start oscillating, and it will start contributing to the axion dark matter abundance that we observed today. So if we look at the ALP parameter space, where on the x-axis there is the axion mass, and on the y-axis there is the axiomatic constant that we can relate to the axion photon coupling, for example, then we see that we can draw this orange line in which the axion dark matter abundance produced from standard misalignment account the full observed dark matter. And below this line is actually overabundant. We have to tune the misaligned angle. And however, above this line, the dark matter abundance that we can produce via standard misalignment is actually underabundant. And it's specifically in this region of the parameter space with small FA and so large couplings, we have most of the axion searches. So we would like to have a model that can permit to ALP living in its parameter space, so above the orange line, to explain the observed dark matter abundance. And kinetic misalignment can do so. And this mechanism just relies on a different initial condition. And indeed, we have an initial very large kinetic energy for the axion, so large that permits the axion to overshoot the barriers and rolls above the axion potential. And at some point, it gets trapped in this axion potential once the axion velocity becomes the order of the axion mass. And if we call T star the temperature when this occurs, if this T star is much smaller than the oscillation temperature that we have in the usual standard misalignment mechanism, then this results in a delay of the axion oscillations, and this delay means less redshift for the axion energy density, so an enhancement of the dark matter abundance. And indeed, thanks to this enhancement, axion kinetic misalignment can now populate the upper part of the parameter space of ALPS. But the first question we have to ask ourselves is, okay, but how can we generate this large axion velocity? And to do so, we need two ingredients. The first one is an explicit breaking of the Pecha-Quinn symmetry. So we can introduce these higher order operators, which are suppressed by Planck mass, for example, and we choose large exponent, large n, in order also to avoid the axion quality problem. But to make these operators relevant in the early universe, we need our Pecha-Quinn field to be displaced from the minimum. So this means that it has to achieve very large field values. So in this talk, I'm going to use the nomenclature. So I'm going to call the radial mode of this of our Pecha-Quinn field as the axion. The angular mode is of course the axion, and when we refer to the full complex scalar, we call it the Pecha-Quinn field. So there are already several model implementations of axion kinetic misalignment, in which the displacement of the axion field is achieved during inflation. And for this reason, I will refer to them as pre-inflationary models. And the displacement is easily achieved via quantum fluctuations if the Hubble parameter during inflation is larger compared to the axion mass. And also we can use Hubble-induced terms or couplings to the inflaton. And this the effect that we have is to produce a tachyonic mass for the axion, and this mass can then provide a new minimum in the potential at very high field values. And so during inflation, the axion will move away from the origin of field space to regions where higher order values can be relevant. And once after inflation, the field starts moving, also the axion field will experience this angular gradient. And so effectively, we have that once the axion field moves, we get a kick also in the angular direction. And now the axion field will redshift back to the minimum rotating in field space. So in our model, we just rely on this action where we can easily recognize the Einstein gravity and inflationary sector, a kinetic term for the Pecha-Quinn field, and a new ingredient, which is the non-minimal coupling to gravity, which I want to stress is quite natural in this EFT, since it is U1 symmetric and also can come from group renormalization in Cover spacetime. And also we get our usual spontaneous symmetry breaking potential, which we are going to choose to be a quartic potential, and the explicit symmetry breaking potential that we need to generate the axion velocity. And also we introduce a new ingredient, which is the presence of a kination era right after inflation. So let me just spend one comment about this. So a kination era after inflation is something that is already known I think from more than 20 years. And there are some inflation models that can produce this era, for example, some quintessential inflation, in which we have double plateau in the inflaton potential. And in this part of the potential, the inflaton is dominated by potential energy, and it can then drive period of inflation in the universe. Then at some point it encounters this stiff part of the potential, it accelerates and it transfers this potential energy to a kinetic energy. And the energy density, the kinetic energy has an equational state which is equal to 1. So a kination era is basically a period of the universe in which the dominating fluid is an equational state equal to 1. And why we want to use this era, and this is because our Ricci scalar, if we write it down in a FRW metric and we plug in the equational state of the energy density dominating the universe, we see that it has a dependence on the equational state. And indeed, if during inflation we have a -1 equational state and during kination we have it 1, this means that at the transition we have a flip in the sign of the Ricci scalar. And in the term that we have in our Lagrangian, this will provide a very large and positive mass for the axion during inflation, or the Hubble, and a tachyonic mass right after inflation during the kination era. The phenomenology of this mechanism has been already studied, and people refer to it as a Hubble-induced phase transition, and I leave here some works. And we want to exploit this mechanism in order to provide a very large field value to our axion field, so to drive it away from the origin of field space. So we study the dynamics of the axion and the axion, and I write down now the full equation of motions. And if we look at the zero mode for the axion at the beginning of the tachyonic phase, so the transition from inflation to kination, so now the axion field will experience a new minimum at very high field values. And if we look at the equation of motion, this has a solution that is indeed growing in time. And this growth lasts until the quartic barrier becomes relevant and it stops this axion. And at a large field value, higher order operator can become relevant and then impart a kick also in the angular direction, so making the axion moving. Indeed, if you look at a top view of the Pecha-Quinn field, we see that the axion starts from the origin and then it gets displaced. And once it is around its maximum value, then the higher order operator can impart this kick, and it will reshift back to the minimum, now rotating in field space. And we can compute the axion velocity that we have at the kick. So indeed, we can also regard the equational motion of the axion as an equation for the conservation of the U1 charge. And indeed, if there is the presence of higher order operator breaking the U1 symmetry, we see appearing this term in the right-hand side of this equation, which means that this higher order operator indeed produce a U1 charge. And we can numerically solve these equations and compute the charge that we produce during the displacement of this axion. And it's interesting the fact that now this charge depends on the direction that the axion selects at the moment of the spontaneous symmetry breaking. So as you can see here, there is a dependence on the angle that the axion selects. And this means that we are going to end up in a universe with different domains in which, since they are not causally connected at the moment of the kick, our suction field will select different directions. And this means that at the moment of the kick, we are going to produce different charges, different axion velocities, also different in sign. Some of them are clockwise rotating, others are counterclockwise rotating. So we are going to have end up in a universe in which we have different domains and different charge inside each of them with different values, so in modules and also in sign. Now, how can we compute the dark matter abundance in this scenario? What we do is something really close to what happens in the post-inflationary standard misalignment. So in that scenario, we average on the different axion field values that we get in the U1 range. In this scenario, we can average on the different domains. And so we average on the variance of all the U1 charges. And this charge then is converted at the moment of the axion trapping, when late time the axion will experience its own axion potential, then it gets trapped. And there is a transfer of this U1 charge in an axion number density. And I want to stress the fact that this happens regardless the sign of the U1 charge. So if we are going to have, as you expect, net global charge, which is 0, actually a non-zero variance can then be transferred to an axion number density. And then this will result in an axion dark matter abundance. Where here, I just express it with a dependence on the average axion yield, which will depend on the scenario we consider for our cosmology. So in our paper, we take into account two possible scenarios. The first one is the one in which the axion is responsible for the reading of the universe. So at some point, due to the slower redshift of the axion, it will dominate. And after dominating, it will decay into a standard model plasma via an Higgs portal. And in this scenario, we can identify this region in the parameter space of Alps, in which we can explain the observed dark matter abundance via this mechanism. And surprisingly, the average axion yield now, it just depends on the quartic coupling and this asymmetry factor that just parameterize how efficient the kick is. So how efficient is the production of this U1 charge. If you want to know more about this, we have an appendix about the asymmetry factor in our paper. And a second scenario that we consider is the one in which the axion field is now just a spectator, and it will never dominate the energy density of the universe. But in this scenario, it's crucial that the axion gets damped. And this is just to avoid an overclosure problem or a late decay of axion into axions that can spoil the prediction of BBN or Big Bang nucleosynthesis. And for this reason, we impose that the damping of this axion occurs after the rating, since we want to rely on a thermalization of this axion. So for consistency, we ask to happen after rating. And at the same time, it has to happen before that the axion dominates, or before that the axion gets trapped in the axion potential, and especially before that the axion decays into axions. So a first possibility is the thermalization via fermion scattering. We can introduce some case-visitor-like fermions, which are common in UV completion of axion models. And these fermions are indeed charged under QCD, so they efficiently connect this axion to the standard model plasma, and then they can dump the axion energy density via these scatterings. And another possibility is the thermalization via Higgs. And also in this case, as showed you before, the suction field can efficiently be dumped. And in particular here, we also, this kind of coupling introduce a mixing angle with the standard model. So the suction field can be in contact with the thermal buff also at late times after the Higgs boson suppression. And indeed here, I want to stress some pros and cons of these two damping mechanism. Indeed, in the first one, we have a very efficient mechanism that happens at high temperature. But however, the suction can freeze out, since the case visit-like fermions at some point are boson suppressed, and the whole interaction that the suction has with the standard model plasma is via loop-induced process with gluons. And then they can freeze out and eventually can decay into axions, and this can lead to too much dark radiation. And while with the thermalization via Higgs, we have this mixing angle that keep the suction in thermal equilibrium until boson suppression. But at the same time, this coupling requires a tuning of the Higgs mass, since the suction will will keep a VEV at late times. And with this, I show you the parameter space which we have in this scenario. And here the average yield depends on all the parameters we have in the model. So in order to visualize the parameter space, we just project on a two-dimensional slice MA FA2-1 our parameter space. So what you see here is just the maximally allowed parameter space, letting these parameters ranging in these intervals. And with this, I leave you with my summary, and thank you for listening my talk.